start. Today it's a pleasure to welcome Professor Seridonio virtually to Berlândia to give us a talk. Professor Seridonio got his master's in 2002 and his PhD in 2005 at São Carlos, at USP, São Carlos, at the Physics Institute. His advisor was Professor Luiz Nunes Oliveira. And then after that, he did three postdocs in a row, UNESP, UF Niterói, and INPE in São José dos Campos. And from 2010 to now, he has been a faculty at UNESP Ilha Solteira. And in 2014, he was a visiting professor in Iceland and in Singapore for a month each time. And today, he's going to talk to us about atomic frustration-based twistronics. So, Professor Seridonio, it's a pleasure to have you here. The microphone is yours.
Okay, Professor George, thank you very much for this introduction. And as George mentioned it, I'm going to talk about this concept, atomic frustration, a concept that I will discuss in details along this talk, and in particular, atomic frustration in the twisted bilayer graphene system. So, let's say the precise title about this topic is atomic frustration based twistronics. Okay. To discuss in detail the definition of atomic frustration in twisted bilayer graphene system, before that I would follow some outline which is given by this one. There is an introduction. In the introduction, I will discuss basically the Dirac and the Weyl semimetals and the possibilities of breaking some fundamental symmetry, such as time reversal or inversion symmetry. As I'm going to discuss some kind of novel molecular state in the twisted bilayer graphene system, I would prefer to remember some details from the single impurity. I mean, some features from the single impurity in the context of metals. I mean, the Anderson Hamiltonian for a single impurity. And I would like to stress that the physics of the atomic frustration in the twisted bilayer graphene system basically is the physics arising from the from 2D Weyl fermions. So before to discuss 2D Weyl fermions in the graphene, I will spend some time with you discussing the traditional Weyl metals in 3D. Of course, to evaluate some spectral quantities related to atomic frustration, I should mention the approach adopted to estimate this atomic frustration. So I will discuss a little bit about the Green's functions, the equation of motion approach, and a mean field theory, in particular the one given by the Hubbard one approach. And finally, after this background, we can finally discuss atomic frustration in in a twisted bilayer graphene system. Conclude, of course, I have the conclusions about this project. So let me begin with some brief review about the Dirac and Weyl fermions. Okay, this Hamiltonian here is just the Weyl Hamiltonian used in condensed matter. So basically, it has a linear dispersion on the momentum, degree of freedom, and basically the symmetries that this system has can be broken by turning on two parameters. I mean, this one here, the vector Q, is associated with time reversal symmetry breaking, and this scalar one here allows to break the inversion symmetry. Okay, in this case, I'm going to see with you that by breaking the inversion symmetry, instead of a semi-metal, we have then a metal, a Weyl metal. So when these two parameters are turned off, we have the standard Dirac semi-metal. Okay, so here we have the Dirac cones, peculiar for Dirac fermions in 3 dimensions. I would like to call attention to the fact that one Dirac point has 2 Weyl nodes. So in this case, when we preserve time reversal and the inversion symmetries, the Weyl nodes are degenerate at the Fermi level, thus forming the so-called Dirac point. And just to introduce the idea, this quantum number key is simply the chirality. Okay, of the spin along the direction of the linear momentum. So in the Dirac semi-metal case, we have 2 coincident pairs of Dirac cones, and each pair of Dirac cones has a certain chirality. For instance, the blue pair of Dirac cones has negative chirality, which is sketched by this line field here, okay, as a magnetic monopole in the momentum space, while the red pair of cones has positive chirality, okay, as sketched here. Now, let's break first time reversal symmetry. When we break time reversal symmetry, we keep this scalar here equal to 0, while this one finite. So the Weyl nodes appear explicit in the momentum space, and we have one Dirac. We have one pair of Dirac cones placed at plus Q, okay, and other one at minus Q. So time reversal symmetry, when it's found broken, just splits the Weyl nodes, preserving energy, but with distinct momenta in the reciprocal space. Okay. In this situation, as in this one, we still have a semi-metal. This one is the so-called Dirac semi-metal, and this one here is a Weyl semi-metal. However, if we keep instead, if we break instead the inversion symmetry by turning on this scalar here, we simply close the system pseudo gap. I mean, the pseudo gap here coincides with the Fermi level. Okay, so in at the Fermi level, the density of states is zero. It's not finite. So when we break the inversion symmetry, we close the pseudo gap, as we can see here in this last sketch. And instead of a Weyl metal, we have a Weyl metal. So to define later on the atomic frustration, let's keep in mind the following: that we need a Weyl metal. Okay, otherwise we can't talk about atomic frustration. So a Weyl metal environment is necessary to introduce the idea of atomic frustration. Okay, but before
Seridonio, may I ask a question?
Of course, feel free to ask questions during the presentation.
Anyone who wants to ask question, please open your microphone and ask the question.
Okay.
What degree of freedom is represented by the Pauli matrix sigma? Is it spin or could be another degree of freedom?
It's not for spin here. Okay, the spin indeed, I will show later on, appears inside the spinor field operator. Okay.
Okay. So sigma is orbital.
Of course, yes. Orbital.
Okay.
Okay, let's move on. Next slide. So I'm going to talk about a molecule. So before to remember the main aspects of a molecule, I would like to discuss some features of the single impurity Anderson Hamiltonian in metals, of course, because we are dealing with Weyl metals here. So basically, this Hamiltonian consists in a free Fermi electron gas here. We have an atomic part. For the sake of simplicity, the impurity just has a single level, which is the level that hybridizes with the continuum of states from the conduction band. Okay, but these impurities has relation. So there is a Hubbard U term here representing the Coulomb repulsion between electrons with opposite spins, and finally the mixing term that couples the conduction electrons to the impurity. So we have several scenarios where we can apply the single impurity Anderson model. For mesoscopic systems, this impurity is simply called the quantum dot. In metallic surfaces with the impurities, another label for these impurities at atom or adatom. So depending on the physical platform, the impurity can be a quantum dot or an adatom. Okay, and this impurity can be characterized by an on-site measurement given by its local density of state. So the spectral characteristics of this impurity appear in its density of states, its local density of states. So basically, we have a level placed around epsilon d, which is the epsilon d, which is the bare level of the impurity, and a second level appears due to the Coulomb blockage given by the resonant peak around epsilon d plus u. These two resonances appear sketched in this diagrammatic scheme for the bands of the system. And due to the presence of this host, the broadening in each level is present, of course. Okay, so I'm not interested here in the bond effect, because we know that for low temperatures there is resonance pinned at the Fermi level. So I'm worried here just about the Coulomb blockade regime. Okay, so in this regime, the impurity, one single impurity, I mean an atom, is characterized by two levels. Okay, one level associated to ED, and another level associated to epsilon G plus U, not ED. Okay, so and what happens when we have an ordinary molecule? Okay, when we put a second impurity in this scenario, we established a tunneling mechanism, a hopping term mechanism between the impurities, and there will be then at the end a molecule. So instead of, if we make a description using a tight binding for a dimmer, okay, when we compute the local density of states for each impurity, instead of observing a single level epsilon D, we see two levels corresponding to the so-called molecular bounding and anti-bounding states. Okay, so the level epsilon D now splits into bounding and anti-bounding molecular states. So in the context of the Anderson model, we expect that each resonance here, I mean epsilon D and epsilon D plus U, we expect that each resonance also splits in the presence of a second impurity. So when we have a single level per band, we have an atom. When we have two levels per band, I mean below the Fermi energy, I mean this band is the valence band. Above the Fermi level, we have the conduction band. So when we have just one level per band, we have an atom. When we have two levels per band, so we have a fingerprint of a molecule. Okay, so in these panels we just compute spectral densities. The diagonal spectral densities represent on-site measurements of the local density of states taken over each impurity. Okay. And the non-diagonal spectral densities simply represent the communication between these impurities. Communication, in this case, that happens via the tunneling mechanism. Okay, so in these two slides, basically we define which is an atom, and what is an atom, and what is a molecule from the perspective of this spectral of an spectral analysis. Okay. Okay. So before to introduce the twisted Bilayer graphene system, I will discuss some on results from my group with collaborators, in particular in this topic of biometals. the first time that the term atomic frustration appears in the literature is in this paper concerning Weyl metals. This paper was published last year, and I will cite some. I will mention the names of the collaborators here. Here we have my Mizobata. William Mizobata is my PhD student. Sanchez, another PhD student, and Luciano Rico now has a postdoc position in Iceland. Yuri Marx also has a postdoc position in Russia, and some professors collaborating in this paper is Mariana Souza from UNESP at Rio Claro, and the Professor Shelley from Iceland. The abstract is short. I can mention. We theoretically analyze the effect of the inversion symmetry breaking on the structure of the impurity molecular states in biometals. We show that for the case of a highly null central symmetric biometallic host, the standard picture of the alternating bounding and anti-bounding orbitals breaks down, and the qualitatively different frustrated atomic state emerges. This is a consequence of the pseudo-gap closing and the related delicate funnel interplay between intra and inter-impurity scattering channels. So I will give the details behind this abstract here. Okay, so let's try to understand the atomic frustration concept here. Here we have Anderson-like Hamiltonian, but with two impurities. Notice that there is no tunneling term between the impurities, so even this way a molecule is expected to appear because the impurities communicate to each other through the host. So the Weyl fermions, or I mean the Weyl environment, will mediate the communication between the impurities, and even in the absence of a tunneling mechanism between the impurities, we still observe a molecule. Okay, so we consider a pair of impurities placed far apart, and the idea is to detect the electron cloud by an STM tip, okay, to characterize the molecule or the atomic frustrated state. Let's begin with the Dirac metal, where we have both time reversal and inversion symmetries preserved. So the host density of states for 0 per chirality, we have the same for negative and positive chirality. So we still have a Dirac metal with a pseudo gap at the Fermi level. In this case, without any breaking down of the fundamental symmetries, the Dirac cones, if we set the STM tip bias voltage at the energy of the anti-bounding molecular state, we just observe the characteristic electron cloud related to an anti-bounding molecular state. Okay, but when we increase that scalar parameter that breaks the inversion symmetry, changing from a Dirac metal to a Weyl metal, because we close the pseudo gap, we observe a crossover to a final state which is characterized by a highly non-central symmetric Dirac cones, okay, since they represent the cones for a biometal. We detect an electron cloud compatible with isolated atoms. So in this case, we see that the host density of states per chirality is different. So the total density of states exhibits a finite density of states at the Fermi level. And because of this, the electron cloud in two impurity systems is compatible with isolated impurities. So we have the impression that we just decouple the impurities from each other, okay? Because here, without the breaking down of the inversion symmetry, we observe an electron cloud typical for an antibounding molecular state. So we had a molecule, but when we break highly the inversion symmetry parameter instead of a molecule, we have the impression that we observe isolated atoms. I mean, we do not have a molecule anymore. Okay, so
Seridonio,
okay.
May I ask a question? In these three diagrams that you have with the plots of the density of states in color, the one on the left for the Q0 equals 0, is this the ground state? Is the ground state an anti-bonding state instead of a bonding state?
This question is very interesting because I do not have here to show you, but typically, George, we know that the bounding molecular state of a molecule represents the ground state, okay?
Yeah.
But the group here has PRB, a rapid communication published in 2017, where for the first time we placed a molecule inside Dirac metal, and this standard configuration changes.
Okay.
I mean, the anti-bounding is now the ground state of the system.
Okay. Okay.
So this characteristic is a dramatic change in the standard picture of molecules, and is completely due to the relativistic nature of the Dirac metals. Okay? Okay.
So this happens too for a biometal. It's the same thing.
Indeed, it happens for any same metal. It happens in graphene and in the 3D version of graphene, the typical 3D values. It is a characteristic from some metals, relativistic metals.
But for all of them, is it a relativistic effect? No.
What I can say that I see this effect in graphene and Dirac and Weyl same metals. Okay. But if I see the same effect, for instance, in parabolic same metal, I'm not sure.
Okay. 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 Thank you.
Okay. Thank you. So the idea to conclude. So let's keep in mind the following. By analyzing this electron cloud, I'll give you a spoiler here. No? I usually say we have the impression that the molecule is started off. So I introduce the concept now of frustration. So frustration is switched on. So the basic, let's say, introductory idea of atomic frustration is the following. We have a molecule, we have a pair of impurities that seem to behave as atoms, but this pair is still a molecule. So a pair of atoms that behaves similar to atoms, but it is still a molecule, okay, allows to introduce this concept. It is a molecular state atomically frustrated. The molecule wants to split itself into atoms, but the molecule is prevented of achieving that by the Weyl environment. So this is the idea behind the concept of atomic frustration. Okay, and let's study some functions that allow to quantify this atomic frustration. We prefer to look at the local density of states of the host, which basically splits into a background contribution, okay, corresponding to the pristine system, the free system, and a second term arising from the induced terms over the DOS by the impurity. So basically, when J equal to J prime, I mean the diagonal term, essentially the diagonal terms give the on-site measurements of the impurity density of states, while the non-diagonal terms, basically the correlation function, indicates the communication between the impurities. I mean the electronic interscattering between the impurities. And basically, both the diagonal and the no diagonal terms here depend on the impurity Green's function, okay, which appears here in the delta rho JJ prime. These impurity Green's functions here in the theoretical approach are determined following the Hubbard-1 mean field approach. So notice that the correlation function depends directly on the impurity Green's function. So we should evaluate these impurity Green's functions within some kind of approximation. The approximation adopted here is just the so-called Hubbard-1 mean field approach. So I will try to summarize the basic aspects of this Hubbard-1 approach. As I said previously, we need to compute this Green's function here, and when we run the equation of motion approach, we obtain two novel Green's functions. In particular, a Green function of higher order. Okay, and a second Green's function which connects opposite impurities. Okay, this one just connects impurities 1 and 2 or 2 and 1. So running once again the EOM, the equation of motion approach, we obtain 3 novel Green's functions of higher order. So here we should implement some kind of decoupling scheme. So the Hubbard one procedure suggests that we should change this pair of Green's function by this one to this pair, okay? And by performing this approximation, we simply cancel these Green's functions, and we have another Green's functions to compute, which follows once again the same strategy, and we observe once again cancellation, and at the end we just have the 2 Green's function that appeared in the beginning. So we are able to close the system of Green's functions. Okay. With these Green's functions calculated by this manner, we are able to construct some numerical figures to understand how to quantify the atomic frustration. So let's understand quantitatively the concept of atomic frustration. Let's remember that from the definition analysis of the single impurity Anderson model, that we have just a single level per band. I mean, the epsilon d level in the valence band, while we have a level epsilon d plus u in the conduction band. When we put a second impurity in the system, each of these levels splits. Okay? Okay, split. So a molecule is characterized by 4 levels. The ED splitting, the splitting associated to ED, and the splitting associated to ED plus U. We have splittings for each Hubbard bands. Okay? So when we look at the diagonal density of states, we just see the typical signature for a molecule, characterized by 4 peaks, the so-called bounding and anti-bounding and the bounding molecular states. Okay, and the non-diagonal density of states shows the same pattern, but with 2 Fano anti-resonances. But in the totality, we still have 4 states. Okay, each pair corresponding to the splitting of the ED level and the ED plus U level. Okay, so panel A simply summarizes the spectral signatures of a molecule in a Dirac method, which has both time reversal and inversion symmetries reserved. But when we break the inversion symmetry, we observe a crossover from this panel A to the panel D, And notice that these states broadened by the continuum of states from the host start to merge to each other. At the end, we have a complete merging between the molecular states into, let's say, atomically frustrated states. Because at panel D, we have the same picture of a single impurity Anderson model, which characterizes an impurity by exhibiting in the density of states two resonant structures or two states. However, this case does not indeed correspond to the situation of isolated atoms. We know that isolated atoms, I mean, when we do not have a molecule, each atom exhibits the traditional Hubbard bands. I mean, two bands. Okay, and despite of this feature here, suggesting that the impurities are decoupled from each other, if we observe the non-diagonal local density of states, we see that this quantity is finite. So if this quantity is finite, certainly the molecule still exists in the system. So if we look locally to the pair of impurities, I mean, if we perform an on-site measurement of the density of states of the system, I mean over each impurity behaves as atoms decoupled from each other. But if we look locally, I mean to the non-diagonal density of states, we see that this quantity is still finite. So we still have a molecule. So this molecule that locally seems to be independent atoms, but no locally is still a molecule, we just introduce the idea of atomic frustration. A molecule that wants to be divided into atoms, but is, as I said previously, highly prevented by the environment, which is of the Weyl metallic nature. So this is the concept of atomic frustration. This slide is not important to introduce the idea of atomic frustration. And now I'm going to discuss, approaching to the end of my talk, the idea of atomic frustration, in particular in the twisted bilayer graphene system. Okay, this paper was published exactly 1 week ago. Okay, and has the collaboration from my PhD students, Mizobata, José Eduardo Sanches, William Carvalho, and some professors, Professor Figueira from Niterói, and Mariano from UNESP at Rio Claro. Okay, let us see what changes when we consider atomic frustration in the twisted bilayer graphene system. Here, just a slide to communicate that we can stack graphene monolayers differently. So we have the so-called AB stacking or stacking AB. In the literature, this stacking is called Bernal stacking. When we put the A sublattice from the top monolayer collinear to the B sublattice from the bottom graphene monolayer. Okay, and this one just when the A sublattices from both monolayers are collinear. Okay, and depending the stacking employed, the electronic properties change according to the stacking adopted. For instance, in the AA stacking, instead of a bilayer graphene, which we expect to be a semi-metal, by performing this kind of stacking, we have a graphene system which is a metal. Okay, because this kind of stacking, if we perform the time binding calculation, we see that the pseudo gap closes, and we observe a Dirac semi-metal with with inversion symmetry breaking. In the other kind of stacking, I mean the Bernal stacking, instead of having the Dirac cones, we have a quadratic semi-metal. Okay, it is still a semi-metal, but the dispersion is quadratic. So this slide is just to show you that depending on the stacking between the graphene monolayers, the electronic properties can change drastically.
Seridonio, may I ask another question? Sorry, I'm very interested in this subject. I am seeing from the pictures that the bilayer seems to have the chirality well defined.
Yes, indeed, I will show that the Weyl index, okay, plays the role of the chirality degree of freedom.
Okay, so it's not the chirality in the sense of the projection of the spin in the direction of the momentum. It's another kind of chirality.
Yes, indeed it emulates the original definition of the chirality. I will show later on. This quantum number here. Okay.
Okay. If I have a question, I ask you.
Of course, feel free to that. So here we have the pictures found in the famous paper from Pablo Herrero, published in Nature in 2018, where the predicted physics of the twisted bilayer graphene system was confirmed. Okay. So when we stack two graphene monolayers and twist these layers, we observe the so-called Moiré pattern of interference. So here, this pattern is known in the literature as a Moiré pattern of interference. And there is some specific twists, specific angles, which we denominate magic angles, because in certain angles, we observe the formation of non-dispersive bands. Okay, so when we twist the bilayer graphene system in certain angles, the first magic angle is given by 1.08 degrees. we observe a completely flat band, which is a non-dispersive band. And just to establish the connection with the first part of my talk, where I presented the Weyl fermions in 3D, let's notice that when we twist the graphene monolayers, the original pairs of Dirac cones from each layer before the twist, this pair of Dirac cones are coincident. But when we perform the twist, we separate these pairs of Dirac cones from each other. So the twist indeed generates the breaking down of the time reversal symmetry, because the Weyl nodes now are resolved, keeping the same energies, but exhibiting different momenta. So the twist just creates the breaking down of time reversal symmetry in the delay graphene system. Okay, and here I'm interested in investigate atomic frustration when we observe a flat band in the banded structure of the bilayer system. This flat band corresponds to the slope of the Dirac cone, okay, totally equal to 0. And when we perform this twist, there is which we call by mini-Brillouin zone. So in the real space, we have the superlattice, okay, which is the Moiré superlattice, while in the momentum space we have a mini-Brillouin zone, distinctly from the single layer. Okay. Now I'm back into the question from Professor George. In particular, when we apply George through the layers, electric field. Okay, as the bilayer graphene system is van der Waals structure, when we apply electric field through the layers, as depicted in this in this slide, we just obtain at the end opposite voltages in this layer. So an electric field generates opposite voltages at the monolayers because the system is a van der Waals structure. Okay, so according to time binding calculations, which can be found in this physical lectures from 2020, we can notice that by applying an electric field, we just break the inversion symmetry. Notice that this Weyl node here suffers a red shift, while this another Weyl node suffers a blue shift. But each Weyl node is located in a specific corner of the mini-Brillouin zone. So if this Weyl node suffers a red shift, and this one in the other side of this direction suffers a blue shift, perceive that this mechanism is very essentially is the same when we break the inversion symmetry when this point, George, corresponds to positive chirality, and this point here corresponds to the negative chirality. So in the bilayer graphene system, the Weyl index essentially emulates the chirality degree of freedom discussed in 3D Weyl semi-metals and metals. Okay. Keeping this in mind, let's move on. So now I'm interested in investigate the atomic frustration in this system. An important information is that for low twists, the Moiré pattern is still hexagonal. Okay, this 2D materials paper published last week employs the following approximation that we are dealing with low twist angles, and around the low twist angles, the Moiré superlattice is still hexagonal. So the model is based on a tight binding with Vanier orbitals centered around the AB and BA stacking regions. So in this region, there is some kind of superatom which corresponds to the AB stacking. And this is another superatom to the BA stacking. So the model is basically a model for a graphene monolayer, but with a renormalized Fermi velocity, which depends on the couplings between the layers and the distance between the Weyl nodes, okay, in the momentum space. This renormalized Fermi velocity can be found calculated in these physics review letters here. So our model is just a monolayer graphene system, but with a renormalized Fermi velocity. So this system is capable of describing the Moiré superlattice when the Moiré superlattice exhibits an hexagonal pattern as a graphene monolayer. Okay, and by applying an electric field, we break the inversion symmetry. Okay. Okay. Here are some analytical results after performing the Hubbard-1 approximations. Here we have the Green's function, the on-site measurement of the Green's functions of the impurities. Basically, the physics of the atomic frustration here is governed by the local self-energy. Okay, this self-energy here is different, but it causes the splitting of the atomic levels, generating the molecular levels, a molecule formed by, intermediated by the host. So let me discuss the results away from the matched angle. These results away from the matched angle essentially are the same observed in 3D Weyl metals. Okay, before breaking the inversion symmetry, we have the well-known molecular states. I'm just showing here the ED level, the splitting around the ED level. I mean the splitting in the first Hubbard band into molecular states, and the broadening of each molecular state is governed by the imaginary part of the self-energy, the local self-energy, which exhibits pseudo-gap behavior. The peak positions can be renormalized by the real part of the self-energy, of the local self-energy, which has this behavior here. So I would like to call attention to the fact that if the level epsilon d is placed below the Fermi level, it suffers due to the coupling with the Moiré superlattice. It suffers a blue shift. I mean, these levels below the Fermi level move toward the Fermi level from the right. I mean, they suffer a blue shift. In the other side, the levels placed above the Fermi level, I mean the molecular states placed above the Fermi level, move toward the Fermi level from here from left, and here from right. I mean a red shift. So the molecular levels can move toward the Fermi level from left, which this represents a blue shift, while the molecular states placed above can move toward the Fermi level from right, which represents a red shift. So the real part of the self-energy is crucial to understand a new type of atomically frustrated state here. If we increase the electric field, I mean, if you increase the breaking down of the inversion symmetry, we observe the standard merging between the molecular states into a single state, which gives us the impression that the atoms are decoupled from each other, but I ensure that here again we have an atomically frustrated state. Okay, but some peculiar behavior emerges when we consider the matched angle, in particular the first matched angle. Okay, again, in the absence of inversion, in the absence of the breaking down of the inversion symmetry, we observe the standard fingerprint of a molecule given by the molecular states, but now we have a strong blue shift and a strong red shift in the matched angle condition, because the self-energy, especially and its real part, depends inversely on the Fermi velocity, which becomes zero in the matched angle. So the contribution to the renormalization of the molecular states increases in the matched angle condition. So by increasing the breaking down of the inversion symmetry, observe distinctly from a case away from the matched angle, where the molecular levels and at the end still the atomic state both stay around the original bare level, because the real part of the self-energy away from the matched angle does not I mean, is not relevant, can be neglected. However, in the magic angular condition, this quantity here is very relevant, so it renormalizes strongly the molecular levels. And with a highly no-centrosymmetric twisted bilayer graphene system, we observe an entire collapse of the molecular states into a zero mode, okay? An atomic frustrated state pinned at the Fermi level. And this state does not belong to independent atoms, is still a molecular state, because if we compute the correlation function here, we observe that this correlation function is still finite, so the molecular binding is still present. Locally, it has features from features for independent atoms. Okay, I mean just a single peak theory, but no, locally we see that the impurities still communicate to each other through the Moiré superlattice. So in this sense, we have an atomic frustration based twistronics. Okay. To conclude, we have demonstrated that the TBG is a promising candidate to host a molecular zero mode, atomically frustrated, considering the atomic molecules with charge mirror symmetry. The TBG system should be driven into a strong metallic phase, which arises from the broken inversion symmetry, the Dirac cones for the emergent mini-Brillouin zones of the Moiré superlattice. Our findings point out that the Moiré superlattice can be considered as a new platform to build unconventional molecular bindings via graphene twistronics. Here we have some, we had our thanks for the attention. And now feel free to make questions.
Thank you very much, Seridonio, for a very nice, very nice seminar. We are open for questions. Luis left and said hi, bye, that he had to go, but he's going to watch the tape. Probably he's going to contact you if he has questions.
Okay, thank you, Gregorio. Hi, Jesse.
Can I ask a question, George?
Yeah, sure. Go ahead.
Nice talk on Seridonio. I think we have discussed some of the results previously. I still have some questions. Maybe it's a little bit technical. I apologize for that. And to relate to your model, as far as I understand, you model the angle, right? The twist angle. So in the tight bind model, let me think that way. In the tight bind model, the angle probably the information about the angle is included in the hopping, right? The inter layer hopping.
Yes.
But how do you translate that into your continuous model?
Okay, I will try to summarize these aspects you mentioned. The basic idea, Werneck, is to modulate, to describe the Moiré superlattice when this superlattice shows hexagonal pattern. Okay, there are some patterns in the Moiré superlattice that are not hexagonal. So we are restricted to the situation where we have an hexagonal lattice. So this lattice is a superlattice. Okay. In the case of a superlattice hexagonal, we have some results in the literature that teach us to describe this system within a tight binding model. I will show you, but with Wannier orbitals not centered around the AB and not around the A and B sublattices from the monolayers, but a tight bind description with Wannier orbitals around the stacking regions given by the AB and BA stacking. Okay, let me show a figure in this.
But this is still a bipartite lattice, right?
Yes, yes, yes. It is still a bipartite lattice. This one here is like that. Wow. Okay. So there are tight binding calculations in the literature that, as I said, treats the Moiré superlattice as a bipartite lattice, which is hexagonal. So in this approach, in particular, perturbation theory on this system estimates that the Fermi velocity, okay, becomes renormalized, and this renormalization is given by the couplings between the AA sublattices, I mean top and bottom, AB and BA, okay, and it also depends on the distance between the Weyl nodes in momentum space. So the original Hamiltonian is written in the real space. So as we have a bipartite lattice, we can make a Fourier transform and obtain a continuum model, as you said, which is essentially the graphene Hamiltonian, but with the renormalized Fermi velocity instead. That's it. Okay.
Okay, but this is not actually, this is a continuum model, but it's not a low energy. It's not restricted low energy.
No, yes, yes.
Right? We have the full Brillouin song here. No, actually not.
Allow the correction that this model here is still in the low energy approximation, because
yes, because linear in K. Yeah.
Yes, of course. Yes.
But is it continuum? You're in the continuum or in the lattice?
Now I'm in the reciprocal space. I'm in the continuum. Yes.
Okay. Any more questions?
Thank you.
Cernek?
Okay.
I have a couple of questions. In slide 7,
okay,
when you were talking about the fingerprints of the fact that you have a molecule, although it looks like two atoms that do not form a molecule, if you separate the atoms, you would expect then that the ground state energy would go up, right? Showing that you really have a molecule.
Yes. Here, observe that the atoms are very far apart.
Okay.
The distance between them is 20 angstroms.
Okay.
Despite this huge distance, the environment is still connects the impurities.
Okay, yeah, and you have an anti-bonding state. Yes. But my question is, if you separate them even more, you should see this ground state energy, the anti-bonding.
No. We have a result, especially a slide not mentioned, but let me amplify this slide here. This is exactly the case you want to understand. Observe by increasing the distance between the atoms, I mean the length of the molecule, the local density of states induced by these impurities see implications. So these states, bounding and unbounding, disappear. In this case, we have indeed the coupled atoms.
Okay. So, and that shows that in the beginning you really had a molecule, because that's what you expect to happen to a molecule once it's too far away, right?
Right, of course.
Okay.
Yes.
Okay. The other question is, what are the impurities in the model for the bilayer graphene? Are the impurities, are the impurities atoms, or they are like real atoms, or they are something that that simulates one of these, would call them super atoms?
Yes.
That form the superlattice of the bilayer graphene. What is the impurity, or what are the impurities, because there are two, right?
Okay. So I realized that I discovered that you were our referee. So I revealed the identity of our referee.
Okay. I don't know if you noticed that I blushed.
I will explain again this question. Okay.
Okay. I didn't get it.
Okay. This question is very, very interesting, because these physical review letters here from Moiré, published last year, treats exactly this scenario, George. Because if we perform again time binding calculations, we verify that the electrons accumulate in this hollow site. Okay, so the electrons in the twisted bilayer graphene system prefer to accumulate here. So if we put standard impurities, I mean impurities with sizes of the order of carbon atoms.
Okay.
So the two Fermi orbitals centered around AB and BA will overlap simultaneously with these standard atomic impurities. I mean atomic impurities, impurities with sizes of the order of carbons.
Like a cobalt atom or something that people use to see condo resonance in surfaces. Okay.
Yes, perfect. So the idea is to consider an impurity bigger than usual impurities, okay, and to avoid these both overlaps.
Okay.
And put these impurities, for instance, over the AB or BA side. But the sizes of these impurities should be bigger than the atomic length scale, but smaller than the Moiré length scale. So one referee made the same question, and we have proposed that the way to achieve this is engineer some kind of clusters. So
some kind of, sorry, I didn't hear.
Clusters of ions. If you if you put together some ions, you make a cluster, and so you can increase the size of the impurity to be bigger than the atomic length scale of a monolayer, but you can control the size of the impurity to be smaller than the Moiré superlattice. So these impurities are not impurities from the periodic table. We should engineer these impurities, for instance, by building clusters of ions. Okay.
Okay. As I said in my report, I am satisfied with your answer.
Oh, okay. I was afraid with a comment from you now. Okay.
Okay. No, I am satisfied.
Thank you.
Professor Marcos Sergio had to leave. Mariana is thanking for the talk. Does anyone want to ask a question to Professor
Yes,
Seridonio?
I have one.
Oh, I know your voice.
Yeah, Gineton.
Question. Hi, good afternoon, everyone. First, thanks so much for your nice talk, Seridonio. The question I have, actually, I'm not precise if I have missed it because I was having some problem with the connection here. And my question is regard to this magic angle. So some people have reported.
Sorry,
yeah,
sorry, I have to leave now. So keep discussing. Thank you, Seridonio.
Sorry. Could you make again your question?
Yes, I ask the question. So my question is in regard to this magic angles, because there are some works reporting that for some specific magic angles you can see some superconducting states, right?
Of course,
so
yes.
So have you taken this possibility in your magic angles and calculations, or you're not taking into account?
Okay. If you see the papers from Pablo Herrero from 2020, which are two papers. The first one discusses the insulating phase, and the second one discusses this possibility of having superconductivity. And the basic, the fundamental ingredient to have superconductivity is to dot the twisted graphene system. So we should break the degeneracy between the Fermi level and the Dirac point. In this paper here, we do not allow doping, so we still have particle-hole symmetry. So the Fermi level is the same, it coincides with the Dirac point, and due to this characteristic, superconductivity is not possible in our system. But if we move the Fermi level from that point, I agree with you. Yes, the system exhibits superconductivity. Okay.
Yeah. Okay. Yeah. Okay. Thank you so much, Seridonio.
Okay. Thank you.
Did you guys? I have one more question. Did you guys investigate if there is anything interesting regarding the fact that the resonance of the molecule when it moves to the Fermi energy? If I am not mistaken, I'm not very familiar with the twisted bilayer graphene. It should be on top then of the flat band, right? Do you have a flat band? So did you investigate because the flat band could be ferromagnetic if you do if you introduce some perturbation, in general, you see ferromagnetism in flat bands.
Okay.
And I know that they have reported something regarding strongly correlated ground states for some magic angles. And I assume that they could come from that. Besides the superconductivity, they could come from the ferromagnetism in the flat bands.
I think it can be found, but I do not have this effect here because I understand that even break time reversal symmetry, because when we twist, we have this time reversal symmetry violated, and this breaking down of the symmetry could be the source of some kind of magnetism in flat bands.
Okay. Okay.
So, but for instance, Werneck has this paper about Coulomb effect with Weyl metals.
Yeah.
And he sees there that some breaking of the spin degeneracy just occurs approaching to the edges of the bands.
Okay.
Of the band. And despite the presence of time reversal symmetry violated here, the model is low energy, so I can't see this effect of magnetism near the edges of the band. So
okay.
This time reversal could be the source, together with the flat band, for some kind of magnetism, but as I mean within the low energy approximation, I can't see it.
Okay. Okay. Thank you. Thank you.
Mm-hmm.
Any questions? Anyone? We had quite a few already. It's already 3:30. We had a very nice conversation. Mariana, Mariana Lima, thanks for the talk.
Thank you.
And as I said, Professor Figueira had to leave. And so if we don't have any more questions, if there are...
Professor Figueira is a co-author.
Yeah, I saw. Yeah. So he knows what you were talking about. Yeah. So if we have no more questions, we should thank the speaker again. Thank you so much for your talk. I'm gonna be sending you an email very soon asking for the slides, if you don't mind, so that we can post them together with the video in our YouTube channel, and I can send you the link for our YouTube channel, and you can visit there and see. We have I believe all the talks are there. The one responsible for Professor Werneck, I will thank him again for doing that because it's a lot of work.
Okay, sure, I can provide the slides.
Okay.
It will be a pleasure to share with you this content, and thank you very much for this opportunity again. Okay.
Thank you for accepting, and so I think we are done. It was again, it was a very nice seminar.
Okay.
We are sure to invite you again.
Oh, thank you.
Okay.
I'll be waiting.
Okay.
Thank you very much, and see you. Okay.
Okay. Thank you very much, and bye bye.
Bye bye.